Good morning, here we are. It is the physics video lecture. Physics 105B, video lecture 28. So I brought a demo object, namely the gyroscope right there. We're talking about rigid body motion and the Euler equations. So we should have a couple interesting things to talk about here. Yeah, so let's see how to get started. This is our big topic today, Euler equation. So I'll get set up a bit and then we'll do some demonstration with the gyroscope there. So I'm just going to once again write down our inertial tensor dm r squared delta ij minus xixj over the body, for the rigid body, and the diagonal form is always possible, so that's very important. We're going to have very often I1, 0, I2, 0, 0, I3. Because that's always possible, and depending on the values of these, you have different types of tops or gyroscope, whatever you want to call it. So let's go ahead and remind ourselves we have L equals I omega, and this of course is a matrix multiplication. And what do we have for our law of motion? Well, just for a multi-particle system, we had the following expression: dl dt is equal to the torque. So the moment of the angular momentum, time derivative, is equal to the net external torque, net external. So this we had before, but now we have this whole formalism here. So here we would have d dt I omega is equal to this net external torque. And here's where the real problem would begin. Right, omega was introduced because it characterizes the rotation of the body as a whole. So the concept of the angular velocity was not right here. And so at this stage we thought, okay, this is, not so bad with three components. But now we're looking at the fact that I, in the inertial frame, is a function of all these masses and their positions. So it's a function of position and time, okay, in the inertial frame. And so this would be an unimaginably complicated equation of motion. If not unimaginably, then imaginably. Very complicated. Okay. So I'll just put that as a note. I'll just name this star. In the inertial system, where star is valid, the inertial tensor is a function of the time. Now there are ways to kind of get around that, and that's what we're going to be talking about here. Function of the time, so this is actually a very complicated equation. Time, comma, as is omega. So what we're going to do is transform this equation to the body system. And this was already undertaken by Euler. And the equations that result from that are called the Euler equations. So next, transform our equation to the body system. Okay, but before we do that, we'll do a little demonstration on the gyroscope. Because if we're in the inertial system and this lab is the lab system, okay, then dLdt is net torque, and there are a bunch of interesting phenomena associated with that we can inspect with this gyroscope here. So the first thing we want to talk about is if the torque is zero, because then the angular momentum is constant. Okay, and we can do that with this gyroscope. See, this thing is going to have a part that rotates there. Okay, and the center of mass can be adjusted. So if you go here and balance this, and the center of mass is obviously at that point of balance. Easier said than done, but you get the idea, right? We can adjust this. Center of mass is right here, and then we could say the net external torque vanishes. So that's what we're going to look at. Net external torque vanishing, and you just spin this thing up. You don't even have to spin it up that fast. It's a pretty good device. Okay, so spin her up. And point is, net external torque is zero, and the angular velocity and angular momentum vectors are both parallel, pointing in the same direction. Okay, so net torque, net external torque equals zero, L is equal to constant. And since we're along a symmetry axis, L and omega are parallel. Okay. So let's say a couple things about this gyroscope demo. Now that's not all that's possible. So I could set this thing in motion. That's kind of a typical motion right there. Now what we're going to have, we're going to have to calculate this. We still have a net external torque is zero. So dL dt is zero. Therefore the angular momentum is what's constant in this. Let me just kind of do a slow motion of what's happening here. Okay. Well, easier said than done. I think that's pretty visible. I wanted to exaggerate it. There we go. So if the angular momentum is constant, where is it pointing? Well, what we have is an angular velocity vector that is doing this kind of a motion, and the angular momentum vector is right down the center of it. So if you can imagine a cone being swept out by this thing, then the angular momentum vector is straight down the middle of that cone. And motions are even better if you slow things down a bit, because then you can just exaggerate them more. So again, this is still the force-free top. Okay, net external torque is equal to zero, and we're getting some fairly complicated motion here. There's a precession involved. Okay, so let's set that there for the moment. So gyroscope, we have 1 pound net equals 0 because we're in the center of mass. L is equal to constant, comma, but omega is not equal to a constant. Of course, right now they're both parallel. So this should have actually been my second point. So my first point would have been L equals constant and omega is constant, okay? But then when I showed you this other motion, we haven't added any torque to the mix, so that's just a different initial condition to the system. In fact, when it's slower, it's really, you actually can start to see better what's going on. Okay, so that is what we're going to treat today, but I'll show you right now the case where net torque is not equal to 0. Because all we have to do here is unbalance this thing. I'm going to stop it. So we had a balanced gyroscope, but I can bring this weight down to here, and now it's unbalanced. So we'll say it has a net torque. Okay. Now it has a net torque, and I could put this in the other direction as well, have a net torque there. I'll go ahead down here. Okay. So it's unbalanced. And I'm going to spin it up. First I'll spin it up and just hold it. Okay. Yeah, I want a little more speed. Okay, once more with feeling. Okay, let's get this thing going. Oop. Third tries a charm. What's going on here? Okay, there we go. Okay, so if it's spinning and I'm just holding it in place, then we have L and omega pointed in the same direction, that axle there. That's L and omega. But since it's unbalanced, I get a more complicated motion because L is now changing. Okay. The change of L is equal to torque, right? In the lab frame here. So you could say in slow motion, the L is along this basically, and this vector is changing, right? And that change of that vector, suppose it's facing you guys right here, the change of the vector is towards you, okay? Towards you, and that torque is also towards you. You can see that's the torque, the twisting, okay? So this is referred to as precession. And the up and down motion is referred to as nutation. So we're going to work our way through some of this. But the first thing we have to do is the force-free gyroscope. Okay, fantastic. Bring it to a stop. Okay. So we will leave this board up here for now, and this was just discussion of that demonstration. So before we move on, L is not constant. And here's a couple terms. There's precession and there is nutation. You know, before I even go on, since I'm on this topic here, let's look at this unbalanced device one more time. Spin her up and say a couple more words. We have it out. Turns out that our Earth is an unbalanced top, an unbalanced gyroscope. So imagine that that's the Earth. Every rotation is a day. Okay, 360 of those would be a year. Yeah, I'm going to go ahead and draw that right now. Session. Okay, 1, 2. So we'll call this point 3. Earth is an unbalanced gyroscope. Put that that in scare quotes. So what is this? Basically, this is your angular momentum vector, roughly. What's it pointing at? It's pointing at the North Star. So how long does it take for a single precession to occur for our Earth? It takes about 26,000 years, okay? And you can see the nutations have damped out, but the astronomers can ascertain that Earth also has a nutation, so there's that motion going on as well. And the frequency of the nutations is apparently 40,000 years or something large. These motions are coupled with ice ages and other interesting events. Okay, so they're well studied. And let me just put a couple things down for you guys here. So Earth is an unbalanced gyroscope. Let's just go ahead and draw our Earth with the sun is over here, and we know the axis is tilted, about 23 degrees with respect to the orbital plane. So there's the rotation of the Earth. And where does the precession come from? If Earth were a perfectly uniform sphere, then Newton's law would act on it, the sun would act on it just like as if it were a point mass. But in fact, the Earth is an oblate spheroid, so it has slightly greater, okay, so it's not a perfect sphere, it's an oblate spheroid. You guys make a better picture than I'm making, okay? All right, you've got these three axes. So oblate spheroid. That's our Earth, and therefore there's mass distributed out here and out here, and this mass is closer to the sun, and there is, in the sense of those expansions we did recently, there's more gravitational pull on this side than there is on this side. There's actually a little bit of a torque. Okay, you can see there's a sort of a couple here, got more of a pull here than here. You get a net torque, and that's enough to change the angular momentum vector. So it's because of the mass distribution, and that's why we're talking about oblate spheroids and their properties. We need them in terms of the dynamics of the Earth, but we also need it in terms of the gravitational interaction of the Earth, which we did earlier in the semester. So we have the inertial tensor of the Earth, and that's part of our homework, right? But we also have the quadrupole tensor, which is how we would couple the Earth to the sun's interaction. Okay, so you can see all this stuff comes together pretty nicely, and therefore this angle changes, and that's your nutation. Got to ask the astronomers. And then the precession would be that this angular momentum vector sweeps out a cone, but that takes, like I said, 26,000 years. Nutation takes some 40,000 odd years. Okay, very rich topic. So let's come back to our equations of motion now that we see what all the ramifications are. Yeah, good. So I'll leave those up. So we're going to transform that equation star up there to the body system. And that transformation, so transform, I'll just start, transform d dt I omega equals tau to the body system. So for generally, we have this relation dA dt equals d prime A dt plus omega cross A. So we have to do this operation on our equation of motion right here. So let's see. Plus or minus omega cross A. This is fine. So we have d. In fact, I can skip a step. See, in the body system, I is a constant, so this is the left side of our equation for the first part. Then we're going to add omega cross I omega, right, equals tau. So that's the translation. And now we just have to work this out. So this is matrix times vector, and then the cross product of vector omega. So component-wise, so in components, once you write the first one down, you see what's going on, because then you can just cycle through them. We would have this is diagonal. Did I say it's, yeah. So we're using a diagonal, okay. So in components we'll have I1 d omega 1 dt plus, and since the one component it'll be omega 2 I3 omega 3 minus omega 3 I2 omega 2, and that'll be tau sub 1. And you can do the other three cyclically plus cyclic. So that's how they're written down. When we do the force-free, the torque-free one, we let the net external torque be 0. So yeah, you just cycle through 1, 2, and 3 in the same way, and you have all three of those equations. Maybe leave some room and do it in your notes. So we're going to consider the net external torque equals 0, and we can get to the form we're looking for. So we'll have I1 d omega 1 dt. We'll bring the other stuff to the other side, so it'll be it's omega, yeah, I3 omega 2 omega 3 minus I2 omega 2 omega 3. Good. So let's go ahead and fax it out. Minus I2 omega 2 omega 3 omega 2 dt, and you just go through cyclically. Do I have them on this side? Oh, I'm not in agreement. Oh, okay. I2 minus I3, omega 2, omega 3. Yeah. and then so 1, 2, 3, and then 2 I3 minus I1, over 1 omega 3, and I3 d omega 3 dt is equal to I1 minus I2 omega 1 omega 2. So those are the Euler equations for the free top, and for the moment they're actually still pretty complicated, although they don't look that bad. 1, 2. So let's inspect these briefly. What makes them complicated is that they are very nonlinear. They're highly nonlinear. That's, you see, the product of these omega components is as nonlinear as you're going to get, okay? So these are nonlinear equations. Nonlinear differential equations. However, there are special cases. So they're almost trivial cases. Let's just look at them before we write anything down. Suppose I1 equals I2 equals I3. Well, then everything here is a 0. And then the right side of the equation is 0, and therefore your omega is going to be constant. So that's called the spherical top, as we talked about earlier. I1 equals I2 equals I3. Then omega equals constant. So the spherical top isn't just a sphere. Remember the cube. The uniform cube is also a spherical top, and its dynamics are pretty basic because then omega is constant in the body frame, and then omega is going to be constant in the lab frame. So the force-free spherical top is very basic, and we've got that. Okay. So yeah, in fact, we'll add that note. Omega is constant in lab and body frames. We've made use of that theorem a couple times already. Let me check the time here. Good. So they can be as non-linear as they want. In that case, we're fine. So what about the symmetric top? So suppose we have I1 is equal to I2, but I1 is not equal to I3. That's the symmetric top. And that's the one we just demonstrated, okay? You've got the symmetry in this thing. You know, you could let your XY axis be in the plane of this disk here, and then you've got symmetry there, but the Z direction, you're clearly not symmetric. So, symmetric top or gyroscope, the one we've just looked at, and these equations are really nice in that case because I1 minus I2 is 0. And from that, we got 0 on the right side, we get omega 3 is constant. Okay. And from omega 3 being constant, we can replace the constant here and here, and we're left with coupled linear differential equations. So this case is really good. So from I1 equals I2, we obtain d omega 3 dt equals 0, and then we get omega 3 is equal to a constant. So we're going to rewrite these with that in mind. So now, since we have I1 equals I2, omega 3 is constant, we can write d omega 1 dt is equal to I1 minus I3 divided by I1. Okay, 2 and I1 are the same, so I want to say 3 I1. We've got the omega 3 there. I'll put a block around that omega 2, and d omega 2 dt is equal to I3 minus I1. I can pull a minus sign out of here. Minus I1 minus I3 over, divided by I2, but that's I1 again. And we've got the omega 3 again. So I'll put this in here. So this is just some constant times omega 1. So you've got these coupled equations, d omega 1 dt proportional to omega 2, d omega 2 dt proportional to minus omega 1. And those are easy enough to solve. Okay, just trigonometric functions. So we may give this a different name. Let's see what I have in my notes here. Yes, well, I named it omega. I don't know if that was such a good idea. So let's go ahead and define could have been nice to make this the magnitude of the vector, but forget it, we're fine. We're just going to define this as I1 minus I2, I3 over I1 times that omega 3. So we'll define that, and it's probably some detail about whether we take the I1 greater or less than I3, but I'll leave it right there for now. I don't have any absolute value in the definition. That won't change things materially. So for the moment, we'll let I1 be greater than I3. Okay. So I1 greater than I3. Question mark. As to the ramification, we always come back and deal with that. Good. So what do we have here? D omega 1 dt is equal to omega 2 d omega 2 dt is equal to minus omega 1. Okay. And I think we've dealt with this before a couple times. We'll take a time derivative here. D squared omega 1 t squared and an omega. We've got a d omega 2 dt, which is equal to minus omega 1. Okay. And of course, this we can solve. So omega 1 is equal to, I'll just use some letter here. A cos omega t. And then omega 2 is just going to be a sine omega t. Okay. D omega 2 dt cosine omega 1. Am I missing a minus sign here? Good. So I'll put the minus sign in there. Omega 1 is A cos omega t. I can take that. Yeah, these just differ by a phase, okay? So if I take that particular phase here, then d omega 2 dt is minus A cos omega t. Good. So minus A sine omega t. That's going to start to play a role with these different signs here as well, but at the moment we're not worried about that. So we have those two components, and now let's look at what is omega 3 is a constant, but it's going to be related to these two as well. Excellent. Okay, checking the time. Okay, I'm going to do a couple more points on this. So we have omega 1, 2, and 3. Let's go ahead and draw a diagram. So we could be looking at a rotating disk. Okay. Now this is the body frame, and we know that the omega 3 is constant. Okay. That's our omega 3 along the 3 axis. I'll label this 1, 2, and 3. So what about omega 1 and omega 2? Now we have omega 1 squared. Remember, omega 1 and omega 2 are the projections of omega along these body axes. So omega 1 squared plus omega 2 squared is clearly constant, right? It's equal to A squared. So the projection along these axes here, omega 1 and omega 2, is constant, and it is rotating, okay, because you got cosine and sine omega t. So this constant here, let's see if I can kind of draw that. Here's omega 1, omega 2, but the projection is moving. So this is a projection out in this direction, say. And therefore the vector, let's see if I can use black for that. The vector would be out to here. So this would be the omega, and the omega is apparently tracing out a cone, as we saw. So omega is tracing out a cone, and that's going to be the wobble of that disk. If you were going straight around the symmetry axes, of course, you could just rotate the disk, but that wobble was what we saw with this force-free thing processing around like that. good. So I was gonna assign a couple aspects of this. But first I'll just write down. So this is the projection. Yeah, that's what rotates around. Now we're going to want to transform this back to the lab frame, because both omega and L are going to be moving in the body frame. In the lab frame, omega is going to be moving, but L is going to be fixed. Okay. Once again, so when we have this motion here, bring that into play a bit. When we had this motion here for the force-free top, the L was at the center of that cone and fixed. Okay. Here they're actually going to both be moving. Okay, so that's something we're going to complete next time. I'm not just going to write it down right now. Okay. Okay, good. So much for that. Now I'm going to set up, checking the time. We'll put that off for next time. I'm going to leave it right here for now. What we want to do next time is the case when all three of these moments of inertia are different. And instead of exactly solving the nonlinear equation, we have a different approach to it. But yeah, that'll be one to start out fresh. So for now, we'll leave it right here. And the case of the different signs, I1 greater and I1 less than I3 would be worth leaving a little space in your notes and work that one out as well. Okay, good. See you guys next time.